Define the term projectile. So a projectile is an object that is moving under the influence of gravitational force only. 3.2.1 Calculate the maximum height above the ground that the ball will reach after it was thrown in the air. Let's go through our question statement and hear what is going on. So we have a 25-gram ball that is thrown vertically upwards. The ball leaves the thrower's hand 1.3 meters above the ground with an initial velocity of 7.27 meters per second. On its way down, the ball bounces off a balcony at a velocity of 3 meters per second before being caught at its maximum height after the bounce. Ignore all effects of friction as well as any horizontal motion of the ball. Right, so we're looking for the maximum height above the ground that the ball will reach. As soon as I hear maximum height, I know that Vf is equals to 0. Our acceleration is constant, that is 9.8 meters per second squared upwards. What is Vi, the velocity at which the ball was thrown? Vi is 7.27. What else do we need? We're looking for delta y. This is our unknown. With these four variables, which equation can we use? We're going to use Vf squared is equals to Vi squared plus 2a delta y. Vf is 0. What about Vi? Let's take up as positive. Common sense. So Vi will be positive 7.27 squared plus 2 multiplied by our acceleration. If we're taking up as positive, then our acceleration will be minus 9.8 multiplied by delta y, what we are interested in. So we're going to have minus 7.27 squared being equals to minus 19.6 delta y. We just need to divide both sides by minus 19.6. If we go ahead and do that, we're going to have delta y being equals to 2.7 meters. This is the displacement of the ball after it was thrown vertically upwards. But we want the height above the ground. So our height will be equals to 1.3. It was projected 1.3 meters above the ground. Plus its displacement after it was projected, 2.7. This is equals to 4 meters. That is the answer to 3.2.1. So this maximum height up here is 4 meters. Let's do 3.2.2. So 3.2.2, the time that the ball takes until it bounces on the balcony for the first time. So this is where it bounces on the balcony. We can find the time from the point it was projected until the maximum height. And then we can find the time from maximum height until it bounces off the balcony and add those two times. That will give us the time that the ball takes until it bounces on the balcony. Let's calculate the time it takes to reach our maximum height. So what variables do we have? We have Vi, obviously, 7.27. I don't even know which equation I'm going to use, but I know that after writing the variables down, the equation is going to present itself. So Vi is 7.27, Vf is equals to 0. I have my acceleration, that is 9.8. I'm looking for delta t. It will be straightforward which equation we can use if we have these variables. Vf is equals to Vi plus a delta t. Vf is 0. Vi, that is 7.27, plus the acceleration minus 9.8 multiplied by delta t. If we make delta t the subject of the formula, we're going to get minus 7.27 divided by minus 9.8. That will give you 0.742 seconds. That is the time it takes the ball to reach the maximum height. Now we need the time from maximum height until it bounces off the balcony. Well, from the maximum height until the balcony, we have a displacement which is equals to height final 3.2 minus the initial, which is 4. This is equals to minus 0.8 meters. This is our displacement from maximum height until the balcony. What else do we have? We have VI. We know that VI is 0 meters per second. What else do we have? We have the acceleration, obviously, that is 9.8 meters per second squared. And what we're looking for is the time. With these four variables, which equation can we use? Delta y is equals to VI delta t plus a half acceleration delta t squared. So delta y minus 0.8 is equals to VI is 0. So this term is gonna fall away. We are only left with a half our acceleration minus 9.8 delta t squared. So delta t will be equals to the square root of minus 0.8 divided by a half multiplied by minus 9.8, everything to the power a half. This is one term. We need to show that delta t will be equals to 0.404 seconds. So our total time will be equals to 0.404 plus 0.742 plus 0.742. This is 1.15 seconds. Let's do the last question. 3.3. Draw a sketch graph of the displacement of the ball for the entire motion. Use the ground as the reference point. So let's go ahead and sketch our axis. We have the y-axis and we have the x-axis. On the x-axis, we have the time in seconds, and on the y-axis, we have the displacement in meters. We're supposed to sketch the graph of the displacement of the ball for the entire motion. So we start 5.3 meters above the ground. So let's start there. And then we go to a maximum height of 4 meters above the ground. We bounce off the balcony, which is 3.2 meters above the ground. And we go to a new maximum height, which is slightly below the initial maximum height, as we can see on the sketch. What do we need to indicate? The height from which the ball is released. We have shown that it's 1.3, the maximum height that the ball reaches. That is 4 meters. So let's show that. And then the height of the balcony, that is 3.2, somewhere there. What else? The time it takes to bounce on the balcony, 1.15. An object that moves under the influence of the gravitational force only. That is the definition of projectile. If you omit the word object in your definition, you lose a mark. And after gravitational force, if you omit the word only, you lose another mark. So we have to be very precise with our definitions. That is the answer to 3.1. Let's look at our question statement and try answering 3.2. So a 50 grams ball is dropped from a certain height. The velocity time graph below represents the motion of the ball as it bounces vertically on a concrete floor. The time of contact during the bounce is 0.02 seconds. Ignore all effects of friction. And then 3.2, the question says that let's write down the magnitude of the velocity with which the ball leaves the ground after bouncing. So let's look at our graph. Our ball is dropped from a certain height with this velocity right here, which is equals to 0. And then when it strikes the ground, it is striking the ground at 3.92 meters per second. And then it spends 0.02 seconds in contact with the ground and leaves the ground with a velocity of 3.43 meters per second upwards. So the answer to 3.2, we're looking for the magnitude of the velocity with which the ball leaves the ground after bouncing. That should be 3.43 meters per second. And 3.3, draw a labeled free body diagram showing all the forces acting on the ball at 0.77 seconds. So let's go to 0.7 seconds and see what is happening. So at 0.77 seconds, our velocity is equals to 0. we know that we are at a maximum height. But apart from the velocity being equals to 0, there is nothing special about maximum height. Gravitational force is still acting on the object. It is still 9.8 meters per second squared downwards. So our free body diagram should look something like this. We have FG, right? And that is all that we are required to do for 3.3. Now let's move to 3.4 and look at 3.4.1. Use the information given on the graph and calculate the acceleration of the ball. So 3.4.1, we're looking for the acceleration of the ball. There's two ways we can use to answer this question. We can use equations of motion because we have VI, we have VF, and we have delta T. Another way we can find the gradient of our graph. The gradient of the VT graph will give you acceleration, and then the area will give you the displacement. So if we use equations of motion, our VI is equals to 0 meters per second because our ball was dropped, and VF is equals to 3.92 meters per second, the velocity at which we strike the ground. Then the acceleration is what we're interested in, and the time for that motion is 0.4. So if we use equations of motion, we're going to have VF being equals to VI plus A delta T. We say that VF is 3.92 and VI is 0 because it is dropped, right? Plus A multiplied by 0.4. It's easy to see now that A is just equals to 3.92 divided by 0.4, of which if you put in your calculator, you're gonna get 9.8 meters per second squared. So that is our acceleration using equations of motion. If we decide to use the gradient, we can take this first point here, we can take this point and this point and find the gradient between the 2 points, of which we're gonna get y2 minus y1 divided by x2 minus x1. y2, that is 3.92, and y1 is 0. x2, that is 0.4, and x1 is 0. Again, you can see that we're going to get 9.8 meters per second squared, regardless of which technique we decide to use. 3.4.2. The question is saying that let's calculate the height from which the ball was dropped. Again, two ways of answering the question: equations of motion or the area under the graph. For the position or for the displacement, we need the area under the graph. So also to find the height, we're going to use the area under the graph. For the acceleration, we use the gradient of the VT. So you need to know which to use when. We don't just calculate the gradient all the time, right? So if we use the area under the graph, we're going to have area being equals to half base multiplied by height. So the area which we're interested in, let me just erase this. The area which we're interested in is this very area here, is this area we have here. So if we decide to use that area, our base is 0.4. So we have a base of 0.4. And our height is 3.92. Our height is 3.92. The height of our triangle is 3.92. And then if you punch that in your calculator, you should get an area of 0.784. So our answer here will be 0.784 meters. That is the height from which our ball was dropped. Light work. Obviously, you can use equations of motions again to answer these questions. There's multiple ways of solving this one. I think there's probably 5 ways you can use to answer this question. The next question, 3.5. On the same set of axes, draw a position time graph for the motion of the ball from 0 second to 1.12 second. Use the ground as zero reference, indicate the height from which the ball was dropped, and all the relevant times on the t-axis of your graph. So let's go ahead and try that. What do we need? We need our set of axes. We need a set of axes. So our y and our x. We are good to go now. We can say that this is y in meters and this is time in seconds. So our maximum height where our ball was dropped, that is 0.784, and we strike the ground after 0.4 second. We're in contact with the ground for 0.02, so we leave the ground at 0.042 seconds. So let's just plot that first before we carry on. So if we connect those two, we should have something like this. And then our ball will leave the ground. Obviously, it reaches another maximum height. We can see that from our velocity time graph, right? It reaches another maximum height, and then it goes down to strike the ground again. So there at the maximum height, we have a time which is 0.77 seconds. Here it is right here. And then the entire time for the motion is 1.12 seconds. And I think we get to go. I think we've indicated all that we needed to indicate. Let's look at 3.6. Give one term for the rate of change of momentum. What's happening here? So the rate of change of momentum, delta P divided by delta T. We know fully well that this is equals to F net. So the one term which we should give is net force, right? If not net force, then at least resultant force. Yeah, there isn't anything else we can say there. 3.7. Calculate the magnitude of the force exerted by the floor on the ball for the time of contact. So let's go to a graph and look at that. Yeah, let's just erase this. So we're interested on only this part of our motion. We're looking for the force that the floor exerts on the ball. But let's just sketch or draw the free body diagram of the ball while it is in contact with the floor, so that we can have a bit of clarity. So if we do that, we're going to have Fg. Obviously, as free fall is the motion of an object where the only force acting is gravity. Alright, so that is 3.1. Let's go ahead and do 3.2.1. So the question is saying that let's calculate the time taken for ball A to strike the ground. So let's look at ball A here. It is released from a height of 15.2 meters above the ground. When it is released, we know fully well that VI is equals to 0 meters per second. Right, and we have delta Y. So let's take up as positive. If we take up as positive, then delta Y should be equals to minus 15.2 meters when our object strikes the ground. Another information we have is the acceleration, as we always do, minus 9.8 meters per second squared. And what are we looking for? We're looking for the time it takes the ball to strike the ground. Right, so based on the variables we have, VI, acceleration, delta Y, and the time that we're looking for, it's easy to see now that we're going to say delta Y is equals to VI delta T plus a half A delta T squared. Right, initially I didn't want to use this formula because what about delta T squared and delta T? I'm going to have to solve this by factorizing, right? But then I realized that vi is equals to 0. So this term here is going to give me 0. I'm not going to have so many issues, right? So if we go ahead and substitute, we're going to get minus 15.82 is equals to vi, which is 0, right? Multiplied by the time. So that term falls away. Plus a half. The acceleration is minus 9.8 and the time is what we're looking for. So we're going to have minus 15.82 being equals to, this term falls away. We just have minus 4.9 delta t squared. So it's easy to see now that delta t will be equals to the square root of 15.2 divided by 4.9. Right, so now it's just a matter of putting that in your calculator, and what am I getting? I'm getting 1.76126 seconds. So that is the time it takes ball A to strike the ground, right? It makes sense because it's gonna take about 1 second to cover 9.8 meters, right? And then the rest of the height can take less than a second, right? Let's do 3.2.2. So in 3.2.2, quite demanding one, right? 5 marks. We're looking for the magnitude of the velocity with which ball B was projected from the ground. So let's look at the information we have. We don't have VI. If you take the motion from the time it was projected to the maximum height, you can say you have a VF, which is equals to 0, right? But we don't know the maximum height also, because at this point, what we have is the initial velocity, which is unknown, and the acceleration, which is minus 9.8 meters per second squared. And then another thing we can calculate is the time for the motion of ball B, right? Because we are told that ball A and ball B, they strike the ground at the same time. But then when ball A was at this point, that is only when ball B was projected upwards. So we can say that the total time of ball A minus the time taken by ball A to go from maximum height to 3.2 meters below the maximum height will give us the time for ball B, right? So let's go ahead and do that. So for ball B, not ball B but ball A, we can say that delta y is equals to vi delta t plus a half a delta t squared, right? So now our delta y, we can say that is minus 3.2 meters because we're looking for the time taken for only this journey. That is the time we're interested in, right? We're going to subtract it from the total time, and that will be the time for ball B. All right. So if we substitute minus 3.2, then our VI 0 delta t plus a half minus 9.8 delta t squared. Right. So we're going to have minus 3.2 being equals to minus 4.9 delta t squared. If we make delta t the subject of the formula, we're going to get 3.2 divided by 4.9. We know that minus and minus, they're going to cancel out, right? And our time will be 0.8. So we have 0.8081. So right, the time for this part of the motion from this point to this point is 0.8081, right? So to find the time for the entire motion of ball B, we can say that so the time for ball B, we're going to say that it is equals to the total time for ball A, which is 1.76126 minus 0.8081. Right, so let me just put that in my calculator real quick so that I can see what I get. I'm getting 0.95316 seconds. Right, so that is the total time for ball B. Let's revisit the information we have for ball B and see if we can manage to find that VI. We have the time for the total motion, right? We can put that in mind. And then VI is still our unknown. We have the acceleration, which is minus 9.8 meters per second squared. But if we take the motion from the ground to the maximum height, we can say that we have VF, right? We have a VF which is equals to 0. And then to find the change in time from ground to 0, we're gonna say total time divided by 2, because the time taken from ground to the maximum height shall be the same time from maximum height to the ground. It is actually wrong for me to put this dot here. We don't know how high ball B is above the ground at maximum height, right? So if we divide that total time by 2, so we have 0.95316 divided by 2. Let me just put that in my calculator real quick. I'm getting 0.47658. So now I have delta T. I have delta T. I have VI. VI is what I'm looking for. I have acceleration. I have VF. So it's easy to see now that I can say VF is equals to VI plus A delta T. VF is 0. VI is what we're interested in, plus our acceleration, which is minus 9.8 multiplied by the time, which is 0.47658. So minus VI is going to be equals to, so I have minus 9.8 multiplied by 0.47658. Right, so I get minus VI being equals to minus 4.6705. And then VI is equals to 4.6705 meters per second. Right, that is the initial velocity for which ball B is projected upwards. Now the last question, 3.3. So on the same system of axes, let's draw the position time graphs to show the motions of both ball A and B from the instant ball A is dropped until the time it reaches the ground. Let's take the ground as the 0 position, right? Because usually they will say let's take the ground as our reference point, and that will lead to a lot of ambiguity. What do they mean? You know, reference point. Are we taking it as 0? What is happening? But then when they say we must take it as the 0 position, that is clear. There is no ambiguity. You know exactly what is expected of you. Right, so the x-axis, there we go. And then obviously on the x-axis, we're going to have the time in seconds. And on the y-axis, we're going to have delta y in meters. Maximum height 15.2. So let's start with ball A, right? So ball A is starting from 15.2 and then it goes down until it strikes the ground, right? It takes 1.76 seconds for that motion. So we have 1.76 seconds, right? And then now we have to go to ball B. So ball B is only projected 0.8 seconds later. So we have 0.8 here, right? Yeah, that is the time at which is projected. And then it goes up to its maximum height, which is less than that of ball A. That's, yeah, it's easy to see. But then they strike the ground at the same time. So I think we should have something like this. I wonder what you guys did. Can you please let me know in the comments if we have the same position time graph? As always, and then the floor is gonna be pushing the ball upwards. So this will be the force exerted by the floor. So that's what we have there. That is our free body diagram. So we can say that F net is equals to F exerted by the floor minus Fg, because they are in the opposite direction. So if we calculate F net and we find another way of calculating Fg, then we essentially have the force that is exerted by the floor. How can we find F net? We know that F net is equals to the change in P divided by the change in T. So at 0.4, we start with a velocity of 3.92. And at 0.42, when we leave the ground, we have a velocity of 3.43. Now it is important to note that it is 3.92 downwards, and then it is 3.43 upwards. So that will be essential when we choose which direction we take in as positive and which direction we take in as negative. And obviously our change in time is 0.02 seconds. So that seems like we have F net covered. We know that the mass is equals to 50 grams. So we have F net covered. Fg, we also have it covered, because you know that Fg is our outermost simple case, right? So Fg, the mass is 50 grams, and the gravitational acceleration due to the Earth is 9.8 meters per second squared downwards, right? That direction is going to come in handy when we substitute. So which direction do we want to take as positive? Let's take up as positive. So take up as positive. Take up as positive. It is just common sense. So in place of F net, let me just write our equation down again. So F net is equals to the force applied by the floor minus Fg. So in place of F net, we can put the rate of change in momentum, right? So the mass will be 50 divided by 1000 multiplied by Vf, which is 3.43 upwards, minus Vi, which is 3.92 downwards. So if it is downwards, we should substitute it with the minus sign if we take it up as positive. So we're going to have minus 3.92. We close that bracket and we divide everything by 0.02. And then this will be equals to the force that is exerted by the floor minus Fg. So what is our mass? Our mass, again, we have 50 divided by 1000 multiplied by 9.8. So that is 9.8 downwards. So it will actually be minus 9.8. Well, we have already indicated that Fg is going downwards by this minus sign right here. So our 9.8, it actually doesn't need that negative sign, because if it has that negative sign, then we have the force exerted by the floor plus the force exerted by gravity, because that minus and that minus will give you a positive. So that 9.8 is actually supposed to be positive. So we have 9.8 here. And now what you are left with is taking this term to the left hand side. And if we do that, we're going to get the force exerted by the floor being equals to. So now let's just drag and drop for the sake of time. So we duplicate that, and then we're going to have plus 50 divided by 1000 multiplied by 9.8. And that should give us 18.865 newtons. Right, 3.8. In 3.8, the question is saying, if a softer ball is used and the time of contact with the floor is increased while the change in momentum remains constant, how will it influence the force on the ball? right? Only increase, decrease, or remain the same. It is going to decrease, so the answer here is decreases. Why am I saying that? We have already deduced that F net is equals to the change in momentum divided by the change in time. So we're keeping the change in momentum constant. We're saying that it is the same. If we increase the change in time, F net will decrease. Why are we saying so? F net is inversely proportional to the time of contact. A ball is thrown vertically upwards from the top of a building of height 25 meters with a velocity of 12 meters per second. On its way down, the ball passes a door which has a height of 1.9 meters and then strikes the ground as shown in the diagram below. And just like we always do, we can ignore the effects of a friction, right? So the first question here is 3.1, which is saying that let's define the term free fall, right? I'm just going to leave that for you. And 3.2.1 is saying that let's calculate the time taken for the ball to reach its maximum height, right? So let's do a bit of conceptualizing here. So we at the top of the building here, and then the ball is thrown up with some VI, which is equals to 12 meters per second, right? And then the ball goes up until it reaches some maximum height. At the maximum height, we know that we will have a VF, which is equals to 0 meters per second, right? And then what else do we have? We know the acceleration fully well. The acceleration is equals to minus 9.8 meters per second, right, squared. So now we have to decide on the direction. We take in up as positive, right? Hence acceleration is minus 9.8. And what we're looking for, we're looking for delta t. So we have this variable here. We have VF, we have VI, we have A. We're looking for delta t. Which formula can we use? It should be easy to see now that we're going to say VF is equals to VI plus A delta t. So what is VF? We're saying that VF is 0. What is VI? It's 12 meters per second, right? So we put it as it is without a negative sign because we're taking up as positive, and then plus A, which is minus 9.8, right? Minus 9.8 multiplied by delta t. So now it should be easy to see that delta t will be equals to minus 12 divided by minus 9.8, right? And yeah, if you put that in a calculator, you should get a time of 1.22 seconds, right? Now we can do 3.22. So 3.22 is saying that let's find the velocity with which the ball strikes the ground. So again, we're going to conceptualize and we're going to look at the information we have and see how we can solve the problem. So we're looking for what? We're looking for the velocity, right? So we're looking for some VF, right? We have acceleration, we always do, right? And then what else do we have? So it's coming from the top of a building and then it goes down to strike the ground. So we have a delta y, right? Our delta y will be equals to minus 25. Why minus? We have taken up as positive, so the direction down it must be minus, right? So we have that there, and then we also have the VI. Let's not forget we have VI that is equals to 12 meters per second up, right? So now we have these variables. We have VF, VI, A, and delta y. Which formula can we use? So we're gonna have VF squared being equals to VI squared plus 2A delta y. So VF squared is exactly what we're looking for. VI is 12, and then 2 multiplied by A minus 9.8 delta y minus 25, right? So here, if we take square root on both sides, we should get VF is equals to 25.1794 meters per second downwards, right? Downwards. Let's put the direction there. Now the only question that is a bit tricky here, I think, is 3.23. 3.23, you have to be yeah, you have to be extremely sober to do this question. So we're looking for the time it took the ball to move from the top of the door to the ground. So let's come to a sketch. So the ball is coming from the top, right? And then we go to some maximum height, and then as we go down, we at the door at some point of time, and then we keep going down until we are on the ground, right? So we're looking for the time that it takes for the ball to move from the top of the door to the ground, right? From the top of the door to the ground. So now let's fill in the information we have and see how we can solve this problem, right? So here we have a VF, which is equals to 25.1794, right? And then here we also know the acceleration. The acceleration is obviously minus 9.8 meters per second squared, right? And then we have delta y. We know the height of the door is 1.9 meters. So we have delta y, and then what are we looking for? We're looking for the time it takes. So we're looking for delta t. So what we can do here, we can calculate the velocity at this point, right? When it's at exactly the top of the door at this point. If we calculate the velocity at that point, we're going to use VF is equals to VI plus A delta T. My favorite formula, right? It's pretty much straightforward. So let's calculate the velocity at that point so that we can use that simple formula. So to calculate the velocity at that point, we're gonna do exactly what we did at 3.2.2, right? But the only difference here is that delta y is not 25, but it is 25 minus 1.9, right? Think about it. I'm sure you're gonna get it. So we're saying that VF is gonna be equals to the square root of 12 squared, right? Plus 2 multiplied by minus 9.8. We're doing what we did in 3.2.2, right? But then instead of our height being minus 25, right, it's supposed to be 25 minus 1.9, right? But then because then we have a minus, we're just gonna add so that we can have a less delta y, right? Think about it. I'm sure you're gonna get it. So plus 1.9 here, right? And if we compute that, we're gonna get VF is equals to 24.4287 meters per second downwards, right? So this VF that we have here is basically going to be our VI, right? For the motion from the top of the door to the ground. So now our favorite formula, we can say VF is equals to VI plus A delta T, right? We're looking for delta T. So if we solve this and make delta T our subject of the formula, we're gonna get delta T is equals to VF minus VI divided by acceleration, right? So VF is the answer we calculated in 3.2.2, right? So that will be minus 25.1794 because we're taking downwards as negative and upwards as positive, and then minus 24.4287, everything divided by 9.8, right? So everything divided by 9.8. So we should get a delta T, which is equals to here we should have a minus. Let's not forget that. So our delta T is gonna be equals to 0.0. So yeah, I think we're supposed to round off to 2 decimal places, so that will be 0.08 seconds. And then yeah, that's how you solve that problem. Obviously there's other ways you can use to solve that problem, but yeah, I'm deciding to go with that one. 3.3, the last question. What is 3.3 saying here? So here we have let's draw a velocity time graph for the motion of the ball from the moment that the ball is thrown upwards until it strikes the ground. Use the ground as zero reference. Clearly indicate the following on your graph. So let's just have our set of axes first. I'm just gonna do them with a free hand, right? So we just trying to get this over and done with. So we have V here in meters per second, and then we have the time in seconds, right? So we're taking the ground as our zero reference. Okay, fine. And then we must indicate the velocity at which the ball is thrown upwards. The velocity at which the ball is thrown upwards. It's thrown upwards at 12 meters per second. Right? Let's indicate here that we're taking up as positive still. So here at 12 meters per second, our ball is thrown upwards, right? And then it takes 1.22 seconds to reach the maximum height, of which the velocity is 0, right? So here we must have a time which is 1.22, and then from there on, what happens? It changes direction, right? And now we have a negative velocity, so our graph should keep on going down. That line must be straight. The line must be straight. Let me make sure that it's straight. So we have a straight line going there until we reach a velocity of 25.1794, right? With a negative value. So we have minus 25.1794, right? That is the velocity at which we strike the ground, right? And yeah, I think this should be it. How do we define the term free fall? Free fall is a motion of a body where gravity is the only force acting upon it. It is the motion of a body where gravity is the only force acting upon it, right? So let's jump straight to 3.2 and do 3.2.1. So 3.2.1 is saying, let's calculate the speed at which ball A hits the ground. So now let's go through our information and see what is happening here. So we are told that a learner drops a ball from a height of 8 meters. So before we go any further, we know that VI is equals to 0 meters per second, right? Because the ball is being dropped. And then let's choose our direction that we're taking as positive, right? Take up as positive. Let's just go ahead and take up as positive. And then the ball was dropped from a height of 80 meters, and we want the velocity at which it strikes the ground. So we have delta y being equals to minus 8 meters, because the ball is going down and we're taking up as positive, right? Which other information do we know apart from that? We know fully well what acceleration is. Acceleration will be minus 9.8 meters per second squared, right? And then what we're looking for is VF, right? So now we have these 4 variables. Which equation can we use to find VF? It will be easy to see that we're going to say that VF squared is equals to VI squared plus 2a delta y, right? We are governed by the information we have and nothing else. So VF is going to be, VF squared is going to be equals to 0 squared plus 2 multiplied by minus 9.8 multiplied by delta y, which is minus 8. So we're going to take square roots on both sides, right? So let's take square roots on the left hand side and take square root on the right hand side. So if you compute that, you're gonna get VF being equals to 12.52 meters per second downwards, right? We must not forget that we're talking about the velocity at which the ball strikes the ground, right? So that's how we would essentially solve the problem. And then now 3.2.2, so let's do 3.2.2. let's calculate the speed at which ball B was thrown downwards. So let's go ahead and look at the information that has to do with ball B and see what's going on. Our statement continues to read as follows. After 0.6 seconds, another learner throws a second ball B downwards from the same height. So we have the same height, right? So we have delta y still being equals to minus 8 meters for ball B. And what else do we have? We are told that both balls A and B, they hit the ground at the same time. Both ball A and B hit the ground at the same time. So let's put some thought into that and see what is happening, right? So ball A was dropped first, and then after some time, ball B is being dropped, but then they hit the ground at the same time. So clearly, ball B must be moving faster than ball A if it's thrown 0.6 seconds later and they hit the ground at the same time. So what are we saying? We're saying that delta T for ball B will be equals to delta t for ball A minus 0.6, right? It was only thrown 0.6 seconds after, and they reached the ground at the same time. So we can sort of find delta t for ball B by using delta t for ball A. So up to so far we have the displacement and the time, which we can calculate, and we have the acceleration. The acceleration is always going to be equals to minus 9.8 meters per second squared. And then what are we looking for? We're looking for VI. So we have 4 variables here. There's obviously an equation we can use to find VI from these variables. But then first, let's find the change in time for ball B using that of ball A. So let's go ahead and look at the information we had for ball A, right? We have VI, we have VF, and we have A. So we can say that VF will be equals to VI plus A delta T of ball A, right? We are interested on ball A here. So what is VF? VF is minus 12.52, right? So the velocity at which it strikes the ground, and then it's dropped. If it's dropped, VI is 0, and then acceleration is minus 9.8, and then we're looking for delta T of ball A. So real quick, you'll realize that delta T for ball A will be equals to minus 12.52 divided by minus 9.8. So we just have minus 12.52 divided by minus 9.8, which will give us 1.2776 seconds, right? So now we can go ahead and say that delta T for ball B will be equals to 1.2776 minus 0.6, which will be equals to 0.6776 seconds. So now we have delta T for ball B, right? So since we have delta T for ball B, we can then, using the information for ball B, say that delta Y is equals to VI multiplied by delta T plus a half A delta T squared, right? So what is delta Y? We know fully well that that is minus 8. And then what is VI? VI is what we're interested in, right? And then delta T, 0.6776, and then plus a half minus 9.8 multiplied by 0.6776, right? So we're solving for VI. So if we make VI the subject to the formula, we're going to get VI being equals to minus 8, and then we take this term here to the left hand side. If we take this term to the left hand side, then this minus here will be a positive, right? So we're going to have minus 8 plus a half multiplied by 9.8 multiplied by 0.6776. We're supposed to have squared here. Because it's a half A delta T squared, and then everything divided by the coefficient of VI, right? So we're supposed to have squared here too, which is 0.6776. So let me just go ahead and put that in my calculator real quick and see what I get. So I have minus 8 plus a half multiplied by 9.8 multiplied by 0.6776 squared, and then everything divided by 0.6776, and then I'm getting an initial velocity of minus 8.4861, which is just 8.4861 meters per second downwards, right? Downwards. Let's go ahead and calculate the answer for 3.3. So we have 3.3, which says that ball A bounces off the ground to a maximum height of 6.5 meters above the ground. So let's calculate the velocity of ball A as it bounces off the ground. Now we're considering the motion from the time it bounces off the ground until it reaches its maximum height, right? So we know fully well that when it reaches its maximum height, we have VF is equals to 0 meters per second, but we know that acceleration is still minus 9.8 meters per second squared. And then now we have a delta y, which is equals to 6.5. Now we have 6.5 meters. And what are we looking for? We're looking for VI, right? So from the variables we have here, it should be easy to see that we can say that VF squared is equals to VI squared plus 2A delta y. So what is VF squared? That is 0 maximum height. And then what is VI? It's what we're looking for. And then plus 2a minus 30.8, and then delta y, that is 6.5, right? So if we make VI the subject of the formula, we're gonna get minus VI squared being equals to 2 multiplied by minus 9.8 multiplied by 6.5. So we can just divide both sides by minus 1, right? So that we can get rid of this minus on VI squared. So if we do that, VI is going to be equals to the square root of, so we have the square root of 2 multiplied by 9.8 multiplied by 6.5, which will be able to get an initial velocity of 11.29 meters per second upwards, right? Because that's the velocity it bounces off the ground with. And then now to the last question, 3.4. 3.4 is saying that let's sketch a velocity time graph for the motion of ball A from the moment it was dropped until it reaches its maximum height after the bounce, right? So let's go ahead and sketch our axis and see what we can do here. So we have the y-axis, and then we have the x-axis, and then on the x-axis we have the time in seconds, and then on the y-axis we have the velocity in meters per second, right? Yeah, we're supposed to have something like this. And then our starting point, the ball is being dropped, right? So we must start with a velocity of 0 then, and then after that it starts going down, and then its velocity is increasing. So since we take it up as positive, we must have something of this manner, right? And then it's going to strike the ground at 12.52 meters per second, right? So this is the point where it strikes the ground, and then it bounces off. When it bounces off, now it has a positive velocity of what? Of 11.29. So we're supposed to have 11.29 here. And then it starts going up until it reaches a maximum height, and the velocity is equals to 0 again. And that's essentially our entire motion. Let's look at 3.3 before we can even solve 3.1 and 3.2. So 3.3 is saying that let's calculate the time from the moment that the disk C was thrown upwards until the time ball B hits the disk. Right, so we're looking for the time where the two objects strike each other, right? This is one of the most complicated questions you can find in vertical projectile motion, right? But then before we solve the problem, let's do 3.1 and 3.2 first. So 3.1 is a definition. Let's explain the term projectile. I've came across a few cases where people confuse projectile and free fall. So what is the difference between projectile and free fall? Projectile is an object, and then free fall is a motion. So the definition of projectile says that it's an object in which the only force acting is gravity, an object in which the only force acting is gravity. And then free fall, on the other hand, it is the motion of an object in which the only force acting is gravity. So the only difference is that projectile, you just start with an object in which the only force acting is gravity. And then on the other hand, free fall is the motion of an object in which the only force acting is gravity. Right. And let's move to 3.2. So 3.2.1, we have a question saying that let's calculate the time taken by disk C to reach its maximum height. So let's look through the information we have and see which formula we can pick, right? So we can see from our sketch that disk C was thrown up with an initial velocity of 15 meters per second upwards, right? So let's take up as positive, right? And then we're looking for the time it takes to reach maximum height. So we know fully well that at maximum height, VF is equals to 0 meters per second. And then we also have the acceleration, which we always do. It's going to be minus 9.8 meters per second squared, right? As we're taking up as positive, everything going down should be negative. And then what you're looking for is delta t, right? So you can see from these formulas that we have here that we're going to use VF is equals to VI plus A delta t, right? You don't just pick a formula, you are guided by the information you have. So VF is equals to 0. What is VI? VI, it is 15 meters per second plus our acceleration, which is minus 9.8 multiplied by delta t, right? So it's easy to see now that delta t is going to be equals to minus 15 divided by minus 9.8, right? We just took 15 to the left hand side and then we divided both sides by the coefficient of delta t. So if you put that in your calculator, you should get 1.53 seconds, right? So that is the time it takes disk C to reach maximum height. And 3.2.2 is saying let's find the maximum height above the ground reached by disk C. So let's come to a sketch here so that I can take you through something, right? So we know VI because it is given to us, so we have VI at this point, and then we have some VF somewhere here, right, where the velocity is equal to 0, and then we have delta t for this part of the motion. So with that information, we can attempt finding the distance from the top of our building until maximum height, right? And then with that distance, we just have to add 30 meters. After we add 30 meters, we have the maximum height above the ground reached by disk C. You just don't calculate delta y and not add it to 30 meters, which is a common mistake that I see people doing, right? So let's go ahead and look at our information and see which formula we can use. So we have VI, obviously, because it is given to us. And then now we have delta t, which we calculated in 3.2.1. And then what else do we have? We have acceleration, as we always do. And we have VF, right? And then we have what else? I think that is it. So we can use the formula delta y is equals to VI delta t plus a half A delta t squared, right? So if you're not familiar with the topic, you have to write the 4 formulas we have, right? And then every time when you have a question, you list the variables and then look at your formulas and see which one is going to work, right? So delta y will be equals to VI. VI it is 15 multiplied by the time, which is 1.53, right? And then plus a half multiplied by the acceleration, which is minus 9.8. Delta t, we have 1.53 squared. If you put that in your calculator, you're going to get 11.48 meters, right? So the height will be equals to 30 meters plus 11.48 meters, which will be equals to 41.48 meters. So that is the maximum height above the ground reached by disk C, right? Another formula you could have used to calculate the displacement from the top of the building until maximum height, you could have used VF squared is equals to VI squared plus 2A delta y. We have VF, we have VI, we have acceleration. So that formula could have also worked, right? But then I just chose to use this one so that I don't have to take anything to any other side, because here you would have to take VF squared to the other side. Right, let's move to 3.3, the interesting question, the one we've been essentially waiting for, right? So 3.3 says, let's calculate the time from the moment that disk C was thrown upwards until the time ball B hits the disk. So let me show you something. Let me just get rid of this and let's look at our sketch, right? So let's say these two objects, they strike each other at this point. Let's say they strike each other at this point, right? Sort of, you know, let's say they strike each other 25 meters above the ground, right? We just conceptualize it. I'm not saying that is the case. I just want to show you something pretty cool here. So if you calculate delta y of ball C, right, if they meet 25 meters above the ground, that delta y is going to be -5. And then if you calculate delta y for ball B, it is going to be equals to 25. So you can see here that we have an issue. You cannot calculate delta y for C and delta y for B and equate them to each other. Our formulas calculate displacement and not the distance above ground, right? But then what you can do for ball C is that you can calculate the displacement and add 30. Right? So if you add 30 to the displacement of C, then the displacement of C is going to be the displacement of B, right? So that is what we are going to do here. Delta y is equals to VI delta T plus a half A delta T squared. So this is for our disk C, right? So that delta y will be equals to VI, which is 15 multiplied by the time, right? Multiplied by T, because we don't know the time at which they strike each other. And then plus a half, the acceleration is always -9,8, right? And then multiplied by the time squared. So we have the displacement of disk C, right? Now we have to say plus 30. Right, so that we can avoid that issue I was presenting you with there. And then we're gonna have plus 30. If we simplify this even further, we're gonna have 15t minus 4.9 t squared plus 30, right? And then we can call this equation 1, right? That's for disk C. Now let's go to ball B. So for ball B, we're gonna have delta y, and then let's not copy down the formula again. And then what is VI for ball B? That is 40, right? It is given to us right here as 40 meters per second upwards. And then delta T, instead of just putting T, our question here says that ball B was only projected 0.5 seconds later after ball C was projected, right? So the time for ball B, we're gonna actually put T minus 0.5 because it was thrown 0.5 seconds later, right? And then we're gonna have plus a half our acceleration, which is -9.8, and then T, which is T minus 0.5 for ball B. So let's go ahead and solve this. So if we do that, we're gonna get 40t minus 20, right? 40 multiplied by 0.5, and then we're gonna have minus 4.9, and then we have t minus 0.5 squared. So let's go ahead and solve that. T multiplied by t will be t squared, and then t multiplied by minus 0.5 multiplied by 2, that will be minus t, and then 0.5 multiplied by 0.5, that will be plus 0.25, right? And then we're gonna have 40t, right? And then minus 20, and then minus 4.9 t squared plus 4.9 t minus 1.225. So now we just have to solve that, right? So 40t plus 4.9 t, that will be 44.9 t, and then minus 20 minus 1.225, that will be minus 21.225. And then we have minus 4.9 t squared. And then this is our equation 2, right? So now we can say that equation 1 is equals to equation 2. We have 15t minus 4.9 t squared plus 30, right? Equation 2 is equals to 44. So we're gonna have 44.9t minus 21.225 minus 4.9 t squared. So we're going to take minus 4.9 squared to the left hand side, and then it is going to be plus, right? So this here is going to disappear. So in the meanwhile, we're going to have 15t plus 30, right, being equals to 44.9t minus 21.225. So we can take this term to the left hand side and this term to the right hand side. So we're going to have 15t minus 44.9t being equals to minus 21.225 minus 30, right? If you go and do the math, you're gonna get t being equals to 1.71 seconds. So the two objects, they strike each other after 1.71 seconds. A hot air balloon is rising at a constant speed of 4.9 meters per second. At a height of 80 meters above the ground, a ball is released. Let's ignore the effects of friction. And then 3.1. Write down the acceleration of the ball before it was released, right? So before the ball was released, it's inside the balloon, which is moving at a constant speed. Keyword constant, right? So if it's moving at a constant speed, then we have an acceleration of 0 meters per second squared, right? And then for 3.1.2, write down the acceleration of the ball after it is released. After the ball is released from the balloon, now it is in free fall, right? Because gravity is the only force acting on it. So we know fully well that when an object is in free fall, acceleration is equals to 9.8 meters per second squared downwards, right? That's the acceleration when an object is in free fall. And then moving to 3.2 and 3.2.1. Let's calculate the position of the ball 0.5 seconds after it was released relative to the ground. So we want the position of the ball 0.5 seconds after it was released relative to the ground. So let's gather the information we have and see which equation we're going to use, right? So we know fully well that we're looking for delta y, right? And then what do we have? We have delta t, which is equals to 0.5 seconds. And then we also have vi, right? If we come back here to our question statement, the hot air balloon was rising at a constant speed of 4.9 meters per second. And then that's when the ball got released, right? So vi of the ball is also 4.9 meters per second upwards, right? Because the balloon was moving upwards. So that's the vi, the initial velocity of the ball after it was released. Let's look at the other information we have. We always know that acceleration will be 9.8 meters per second squared downwards, right? So now, looking at this information we have, which equation can we use to find delta y? We can obviously say that delta y is equals to vi multiplied by delta t plus a half a delta t squared, right? So what we can do now is to just substitute. What is vi? We can see that vi is 4.9 upwards, right? So let's take up as positive. Take up as positive, right? So everything that is upwards, we're going to put it with a positive sign, and things that are downwards, we're going to put a negative sign, right? And then delta t, there isn't any of that, right? Time is a scalar. We don't have a direction, so we just put 0.5. And then plus a half acceleration. The acceleration is 9.8, but downwards. So we have to say minus 9.8, and then multiply by delta t, 0.5 squared. This is going to give us 1.225 meters, right? We have a positive value, so this is going to be upwards, right? Upwards, right? So let me explain what's going to happen here. So the balloon is being dropped at this point, right? And then what it's going to do is going to travel up until it reaches a velocity of 0 meters per second, and then after that point it's going to go down until it strikes the ground, right? So after 0.5 seconds, it's 1.225 meters above the point which it was dropped, right? So now we can say that the height above the ground, will be equals to the 80 meters, the position at which the ball is being dropped, right, plus 1.225, the distance it has traveled from the time it was dropped, right? So this is going to give us 81.23 meters, right? So after 0.5 seconds, the ball is 81.23 meters above the ground, right? And then let's move to 3.2.2. So 3.2.2 is saying let's find the time taken by the ball to reach the ground. So if we take VI as 4.9 meters per second, delta Y will be equals to minus 80 meters. The minus sign is because the ball has moved downwards, right? And we're taking upwards as positive. And then we always know what the acceleration is. That is 9.8 meters per second squared. And then the minus sign is to show the direction. What else do we have? I think that's it. And then we're looking for delta t, right? We're looking for delta t. So we can use the equation delta y is equals to vi delta t plus a half a delta t squared. But then if we use this equation, we're going to end up with delta t and then delta t squared being unknown. And then we will have to solve a quadratic equation. And I don't want to do that. So what I'm going to do first, I'm going to find VF using VF squared is equals to VI squared plus 2a delta y. And then when I'm done with that, I'm going to use VF is equals to VI plus a delta t to find the time, right? But then let's do that first, right? So VF squared, so we have VS squared being equals to VI, which is 4.9 squared plus 2 multiplied by acceleration. Acceleration is minus 9.8, and then we have delta y, which is minus 80, right? So what we're going to do from here, we're going to take square roots on both sides, right? So 4.9 squared plus 2 multiplied by minus 9.8 multiplied by minus 80, and then close bracket, everything to the power a half. That's the same as taking a square root, right? And then if you compute that, you're gonna get 39.9 meters per second downwards, right? Downwards. So we know that if we are to use this value again, we have to put a negative sign, right? So now I have VF. I can then say that VF is equals to VI plus a delta t. What is VF? VF is minus 39.9. And then what is VI? VI is 4.9. And then plus a, which is minus 9.8, multiplied by delta t. So we can see that delta t is going to be equals to minus 39.9 minus 4.9, everything divided by minus 9.8, right? And then this will be equals to 4.57 seconds, right? So that's the time taken by the ball to reach the ground. Then now moving to 3.2.3, 3. Let's sketch a velocity time graph for the motion of the ball from the instant it is released until it reaches the ground. So let's go ahead and, sketch our axis so that, we can have a bit of clarity. So there goes our y-axis, and then there goes our x-axis, right? So now we have something of this manner. Then on the x, we know that we need the time, and then on the y, we need velocity in meters per second, right? We're supposed to indicate the initial velocity of the ball, so let's go ahead and put that. We know that we started 4.9, right? We're still taking up as positive, right? Yeah, I tend to just keep one direction. I don't change the direction in the middle of the equation. So I have 4.9 as our initial velocity. What else do we need? We need to indicate the time for the entire motion, right? So from 4.9 we reach a maximum height where the velocity is 0, right? So we come somewhere here, and then from there on the velocity of the ball starts increasing as the ball goes downwards, right? So we end up hitting the ground at some point here, right? We know the velocity at which we hit the ground, that is minus 39.9. So here we're supposed to have minus 39.9, right? And then the time it takes is 4.57, right? So we're supposed to have 4.57 there. And then just like that, I think we have essentially solved all our problems. We just have to